Happy New Year. It's 2/2/22, the year of the Tiger King, and I think it's a perfect day to talk about a very helpful topic, studying sample survey data. So if you joined earlier, I think it's sample survey data is not only useful, but you get paid pretty well if you're good at it. You know, there was that NSF job opening where the salary is pretty nice. So I think the idea of this workshop is to get you up to speed of the different aspects of analyzing sample survey data. And because this is a workshop, if you have any questions, just jump in, you know, don't be shy, whether you want to type the question in chat or you want to speak up through the microphone, don't hold back, just jump in. If you want to tell me to skip slides, go faster, slower, whatever helps you. So I'm Mike. I think I've met most of you, but for those that I haven't had the opportunity to meet before, I'm the statistician here at CCPR. If you know, one of the great thing about the stats unit at CCPR is we offer, you know, no appointment necessary stats consulting. If you have questions about data, some project you're working on, need to figure out what statistical tool or programming or method fits your need, feel free to shoot me an email and we can Zoom and take a look at the problem together. You know, what's nice about CCPR is we work hand in hand and is a complement to IDRI. IDRI has workshops themselves. I mean, we can take a look at some of them right now. There's some good programming ones. I think if later on you need to run the Hopin2 cluster, this would be a good one to go to. Yeah, you want to brush up your Stata skills. I think this IDRI workshop is good to attend. And lastly, if you're a student and would like to formally get course credit, I think here are some courses from the stat department and biostat department that give you a more formal treatment of some of the topics we can only spend an hour and a half on. So, you know, there's sampling, there's survey methods, and social statistics from the stat department. I think they're cross-listed. Some of them are from EPI, you know, depending on the timing. And on the biostat side, something similar, the sampling, finite sampling. If I remember, this gives you like a Bayesian flavor for it. And I think this one is a good one. There's a whole course on imputation. I think Tom Bellin teaches that, which is his bread and butter. So check those out if you're interested. Now, to set the stage, I think this is version 2 of something Andy Lin from IDRI and I put together a couple years ago. Back then, Andy, we gave a side-by-side code through and presentation where Andy took the lead on the Stata implementation of some of the survey analysis. And then I paralleled it with the R version. And it worked pretty well. This time, version 2, we're going to try the same thing. The Stata code is here, the R code is here, and later we'll do a side-by-side split screen. So you can see that whether you're comfortable using Stata or R, they're very similar as long as you keep in mind the important general principle. You know, for those familiar in the background, on the left, you have Questlove from the Roots and the legendary Tribe Called Quest on the right. I think they rarely perform together, but this one instance on camera, they did a show together. So it's kind of like whether you want to do survey analysis in R or Stata, your options are open. So I mentioned that whether you want to code in R or Stata, the most important thing is to keep the central important aspects of survey analysis in the back of your head. That helps you navigate the different steps. And I think that's how I'm outlining this workshop. Total survey error is an idea that Robert Groves kind of conceptualized, and that serves as a backbone to everything. Once we get a good understanding of total survey error, we'll show you how to tell R or Stata the survey design. With that set up, you know, I kind of camouflaged this step where it's kind of bad advice. Don't do it. Don't remove the missing data in your data set. Because if you do that, if you throw away any missing data, your estimates at the end of the day most likely will be wrong. On the other hand, operationally, workflow-wise, just to make progress on your code as a prototype, it's not unreasonable to temporarily throw away missing data just so you can make progress on your code. If you do that, it's very important to revisit that missing data and then impute it later. So that's the point I'm trying to get across, and it will follow the workflow of this workshop. Basically, I think if you've done any data analysis, missing data is a reality. You have to deal with it. It's always the specter or ghost in the background haunting your analysis. But don't let that stop you from making progress on your project. Once you take care of the important parts, revisit the missing data, impute it, and then hopefully move towards the finish line of your project. And you'll see that the steps in R or Stata are very similar.
Hi, Mike. This is Martha jumping in. One of the things I think that's important to talk about here is I think that there's lots of good reasons to impute data, but there are also good reasons not to impute data. And I'm just wondering if you could comment a little bit more about when you might not want to do that.
That's an excellent point.
Because I will say I don't always tell my students to impute stuff that's missing. And in certain cases, it's a great idea, but in other cases, it's not. So right. I just thought that, I mean, you kind of have presented this as, I mean, I think you're making some assumptions about where the data is missing and how the data will be used as part of your recommendations here. But I just want to point that out if there are any students on here that there are some trade-offs to be considered. So I thought you might just, I don't know if you have that in your slides now, but I thought you might want to address it.
Martha just introduced a great segue. I think when we get to this section, we'll break down the 3 scenarios of missingness: missing completely at random, not missing at random, and then the in-between, missing at random. And I think we'll take a more in-depth look when we get to that section. Just as Martha said, it's good to understand when you should impute, when you should not impute. And there's different ways to do that. So thank you for the segue, which I think we'll get to that when we get to this section. But this is Robert Groves. I think he's the only census director that had 2 back-to-back appointments. Usually the census directors only have a 4-year appointment. I think he's the only one in history that, you know, span across 10 years. So that kind of speaks to, you know, the respect and knowledge he has. I think now he's the provost at Georgetown. I found this interesting picture. You know, he's a man of the people. I remember I seen him once, and you would think the director of the Census Bureau would have like a personal driver in a Maybach or a limo and a chauffeur. But, you know, like the common person, he took the metro to work. So Robert Groves, one of his great, I think, frameworks is the total survey error. When you're analyzing survey data from the back end as an analyst, you might just be putting the cart behind in front of the horse. You just want to produce some estimate of an outcome you're interested, whether it's a health outcome. But before you do that, you kind of have to unroll that and see all of the different aspects that go into collecting the survey data. We'll break it down later, but on the left branch, I like to think of it as relating to questionnaire design, asking the right questions about the measurements you're interested in. Is it a health outcome? Is it a policy question? Whereas the right side, it deals with your population you're interested in. Who are you interested in? Is it people? Is it people in specific states like California? Is it the people on the East Coast? Or is your target population about all of America? Or your population might not be people at all. If you're in the auto industry, your population might be cars. So I think the way Groves formulated it is, on one branch, you have all of these issues regarding choosing the right questions you want to study. And on the other branch is picking the right individuals for the target population you're interested in. And they meet in the middle to combine for your survey estimate. What I've overlaid is this dashed line. Everything above it, you can kind of think of that as hypothetical. When you're planning a design, these are some of the mismatches where, sure, you might want every individual in America for your scope of your study, but how do you operationalize it? How do you go actually collecting the data? And once you cross that line, when you're actually going door to door or sending paper mail outs to addresses, that's when you cross over to actually collecting data. And I think this hypothetical versus data line also carries over to the measurement aspect. I'll pause there for a bit. I think it's a lot to soak in when I first encountered this, but this is the really helpful and important total survey error framework that can help you navigate different steps of survey analysis. I see a hand raised in the chat from Jen Delin. Sorry if I'm mispronouncing your name, but if you have a question, feel free to ask it.
Yeah, no worries.
Catch my breath.
Yeah, I was just curious, what if you're aiming to like measure or evaluate a specific outcome amongst a representative like population? Which more likely would you lean towards in terms of a framework?
Great question. Let me repackage that a bit. I think we can zoom in on this section. If you're actually about to plan a study, you know, one of the first questions you need to ask is who do you care about in your study? Is it everyone in America? That's your target population. Then the next step is, how do you go sending the survey out to these people? That's your sampling frame. Do you have a list of every address in America. They're out there. It's called the address frame. You can buy them. The Census Bureau has a special partnership. They have a database of addresses from the Postal Service. So the next step would be, of course, they don't have enough money to go to every single address in that database. So they pick a sample. That sample can be a random sample, simple random sample. It could be a stratified sample. It could be a cluster sample, or you can mix and match and do it in different stages, a multi-stage sample. With that design in mind, then they'll pick like 50 people out of millions in the address. That's all about picking the people and going there. Then you still have to flip over to the other side. What questions do you care about? If you're interested in a health outcome, you need to go through these steps. You know, what's the right question to ask on your survey that captures this philosophical construct you have in mind. I think hopefully that gave you a good picture for now. We'll take a look more in depth in the next slides. And this came out kind of recently to kind of show, related to that earlier question, if you put a lot of effort into designing a great sample and study, it's not only cost effective, but it might even be better than a undesigned study. So I'll pause for a bit and let everyone soak in these sentences. I know it's hard to listen and read at the same time.
Mike, is that referring to the Meng's paradox? Is that the same thing?
Yeah, this was
Okay.
the punchline in this article. Xiaoli Meng, I think, was the dean,
Oh,
or
okay.
still is the dean in the stat department at Harvard. I think before COVID, he gave a talk of like version 1 of this paper. This version 2 is using these. He compares 3 big data COVID collection data sets. One of them is the census COVID household pulse data set. The other data set was from Facebook. And the third data set was a traditionally designed random sample. So I think they did a bake-off and compared and contrast some of the bias, precision, properties of these 3 different data sources. And you know, the eye-popping, shocking thing is comparing 250,000 undesigned respondents did equally as well as like 10 respondents from a well-designed study. So if you're interested, you can take a look. I'm sure there's a lot of assumptions going into this. You can kind of take a more in-depth criticism of the paper at your own time. Well, I got a question in chat, and while I look at that, feel free to ask more questions. Right. So this slide, we're going to focus on coverage error. Let me back up a bit to see where the coverage error falls in the total survey error framework. That would be this mismatch. So Venn diagrams are nice because it exactly gets at coverage error. The blue circle might be the target population you care about. All of the individuals in America. But the purple circle is your frame population. This could be your database of addresses. Now there's a mismatch. There's portions where they're hopefully covered. There might be addresses that are not in scope for the people you care about. You can think of addresses at national parks, Yosemite or Yellowstone. If I'm studying health outcomes of people in America, an address in Big Bear, or not Big Bear, Yosemite is irrelevant to me. It's ineligible. And on the other side, there are people you care about in your study that you cannot access through a database of addresses. The Census Bureau had like a toy example they always go back to. West Virginia is notoriously hard to survey. And people living in West Virginia hit all 4 of these reasons why they're hard to locate. They're hard to find, they're hard to contact, they're hard to persuade, and they're hard to interview. So where the mismatch is, whether it's under coverage, it's ineligible, or double counted, all of that goes into coverage error. The yellow dots is your actual sample. You might have 1, 2, 3, 4, 5, 6, 7. You select 7 people out of the entire population. So that covers 1, 2, 3. These 3 steps in this total survey error flow chart. I'll pause there if there's any questions to this. All right, so weights are important. What's problematic with talking about weights is this one word can have many different meanings. There's a lot of different types of weights, and they all serve different purposes. You can have weights that there's calibration weights that adjust for the mismatch between the sampling frame and your target population. There could be sampling weights that adjust for the people you selected versus the people that are not selected. There could be non-response weights that adjust for people that respond versus the people that don't respond. So, the key idea here is, if going back to this total survey error framework, if you look at your data documentation and get an understanding of what the weights mean, that can help you avoid any missteps on wrongly interpreting what this one word weight means. For example, calibration weights would try to fix this coverage error. Sampling weights would try to adjust for this mismatch between your sample selection, people in your database of addresses versus the 50 people you select. And then non-response weights would be adjusting for this mismatch. Even though you selected 50 people, you send out 50 surveys to them, but only 20 people respond. So when it comes to total survey error and survey analysis, I think these are the 3 important weights that are always in the background. And when you get your data set and you see this one column that says design weights, most likely in the background, it has these 3 aspects integrated into it. Oh, all right. Kind of got ahead of myself. So again, calibration weights would be this, adjusting for this mismatch. Sampling weights would be when you're trying to do inference, going from sample to your target population. If you have non-response weights, it would trying to redistribute the non-responding people, depressing the people that don't respond and moving their weights to the people that do respond. Later, a few slides later, we'll have like a picture that hopefully makes more sense. We'll fly through this. If you ever need statistical consulting, if you're working with a statistician or even with your PI or collaborators, if you're getting a survey data source from the Census Bureau, the Bureau of Labor Statistics, one advice is get the documentation. Control F, look for the design methodology. Try to get a better understanding of how they collected their data, what sample design did they use, what type of weights did they apply. Because going back, when we move on to the analysis stage, we have to tell the program and set it up, whether in Stata or R, what the design actually was. If you ignore the sample design, if you ignore the clustering or stratification, your uncertainty variance estimates are going to be off. Bigger problem, if you ignore the weights, everything is going to be wrong. There was one point I wanted to make. You can see in Robert Groves' diagram, this flow chart is directed, right? The arrows point down. When you select your sample, if it's a probability sample moving from the frame to the sample in this direction, that probability of selection is just like a ratio. You pick 50 people out of 5 million. Call that P. If you flip the direction, if you want to go sample to frame, change the arrow. If you go up, that's what a weight is. And really what that is you flip that probability. The probability is like 5 over 5 million. The equivalent weight would be 5 million divided by 5. I'm glossing over things, but that's like one thing to help you understand the relation between probability of selection, and really you just flip it over, take the reciprocal to create the sampling weight. All right, I think we're moving towards the code parts. Every time you see Arnold's transition slides, I think that's when we'll start diving into the code. Once you get your data and your documentation and get a grasp of how the data provider created this sample survey, the next step is you have to tell Stata or R the actual sample design, right? I'll pause for everyone to absorb what's on the slide. Hopefully the color coding makes sense.
Mike, I have a quick question about the type of survey administered. So I know we're going to be talking more about the coding part here, but in terms of, I guess, going a few steps back and trying to figure out whether we're trying to have an in-person administration of the survey or online, especially with COVID. I know a lot of the surveys were done online. If you could maybe share a few words about, some of the, I guess, pros and cons of each. I know resources is one big thing to think about in that context.
Oh, excellent question. Yeah, I didn't get to mention that at all, and this is a perfect time to do it. So I think the way I understand Esmeralda's question is different modes of collecting your data, whether you use an online survey. Alternative is you can mail out a paper survey to addresses. Another alternative would be you can go door to door and take face-to-face surveys. So I think the way survey analysts or designers talk about it is they think of this as survey mode, the mode of collection. Do you use the internet and do web surveys? Do you use the addresses, you mail out forms? Do you use the addresses still, but you go face to face to collect the responses? You can kind of think of that still needing the designer and the analyst to address this point. If you do a web survey, how do you get a frame of all the people using the internet? You need like IP addresses or a list of email addresses. You need to email them your survey. Then one question to keep in mind is, how does your database of emails differ from the population you care about? I don't know if people watch Shark Tank. One of my favorite characters is Mr. Wonderful Kevin. I think the new season came out and there's a lot of good ideas pitched on Shark Tank, a lot of bad ideas. I was scratching my head why Kevin buys bad idea products on Shark Tank, and sometimes he just does it to buy customer emails. So he'll throw thousands of dollars to get more, to improve his database of emails. So you can kind of think of that as he's improving his email sampling frame. So maybe later when he does something like send out web surveys, he's more confident that he has less coverage error. To the other question, pros and cons, I think I can't answer it now because it depends. The two factors you try to balance is cost and quality, right? One method might be more affordable to do. Usually you're trading off quality. You know, the best option is if you balance both.
Thank you, Mike. That's helpful.
So that covers this frame, but there's a cost quality trade-off here also when you're picking a sample design, which makes its way into the next R slide. The traditional design is a simple random sample, a stratified sample, or a clustered sample. That's color coded here. Pink is a cluster group. Green is a strata group. In your data set, you'll have a column that should say something like cluster ID. You might have an additional column that says strata ID. Here's the conceptual, the similarity is both a cluster and strata, they're just groups. You're forming groups of individuals. But how you're using those groups are different. In a cluster group, you only sample some groups, say 5 cluster groups out of all 20. But those 5 groups you pick, you select all of the individuals in that cluster group. On the other hand, a strata group is, if you have 20 groups in your population, you visit every single group. You go to every 20 group, but within each group, you only sample a few of them. So moving on to the code, whether in Stata or R, that's how you tell the computer what the design means. You plug in the weight. Usually, like I said earlier, the weight is really closely related to the probability of selection. So that's where this sample selection comes in, the blue. The purple is you tell the program if there's any clustering. what group IDs did the data providers use as a cluster group? The green is, you tell the program, is there any Strata groups used? And you can see they're pretty similar. It's one line of R, it's one line in Stata. I'll pause there if there's any questions. So this slide is exactly the same as what you see in the top half. Some of the newer survey data sets give you a variable column that has the Strata ID. There's a column for the cluster groups, and there's a column for the survey weights. If that's the case, then in Stata, you would set it up like this. In R, you would set it up like that. That was what we saw in the previous slide. In older data sets, you might get a data set that instead uses something called replicate weights, where you might have several columns. You might have 20 columns that are each called weight 1, weight 2, weight 20. You have like 20 columns. If that's the case, you'll know you're in this situation. In Stata, you would use these commands to use the replicate weights. In R, you would use this equivalent. So I kind of framed it where older data sets usually have the replicate weights, but I think there are some newer data sets where they also use replicate weights as a concern to protect privacy. If they want to protect very sensitive data, one way to do that is they'll release the data using replicate weights only. Comparing that to if they release the strata, the cluster, and sampling weights, the fear there is you can kind of combine these three variables and it might give away PII sensitive data. It's important to keep in mind. One last thing comparing strata to cluster. So I mentioned they're just groupings. The concept, here's the differences. But one way to remember this is usually if you use naturally occurring groups, you're more likely in the cluster group scenario. For example, if I took a survey of UCLA and every academic department is the group, if I only select 5 departments, but each department I send a survey out to all of its students, that would put you more in the cluster group design, where inside that group, you're subject to have within group correlation. All of the students within the sociology department might have some similarities when it comes to the characteristics and interests. So naturally occurring groups are more likely to have correlated observations within that group, if that makes sense. So I think we'll first move to the first R code. I think we're okay on time. Let's see if this works. Are you able to see a split screen of 2 different code examples? Stata's on the left, R is on the right.
Yes.
Fantastic. So these code examples are there for you in the slides. Andy worked up the Stata, I did the R. Everything before this, I'm not even gonna cover it. It's just setting up your data, cleaning it. The important part is this one line. In Stata, you have to tell the program how the data, the sample design makes its way into your data set. So you tell Stata the weights, and you tell Stata the strata group IDs. It's one line of code. Equivalently in R, it's this. It's what we saw on the slide, right? The same variables used for the strata ID. You tell R what the sampling weights are. This is the quick part. Are there any questions about these two lines? This is step 0 when you're doing a survey analysis. The more interesting parts come next. So let's go to that. And that one line covers this part, right? The representation side. How does the 50 people you sampled relate to the 5 million people in the population you care about? So moving to the actual analysis, these are the type of estimates I'm guessing you care about. Compare means, compare totals, compute totals, compute some quantiles, fit a regression with random effects. Whether you use Stata or R, there are equivalent commands to do all of this. And putting them side by side, which we'll do later, but you can see for yourself now, very similar, right? I highlighted one difference that came up a few weeks ago. I can see both ways. I prefer R for some things. I can also see how Stata is really useful and quick to do other things. In this one situation, Stata is great to produce all of these estimates pretty easy. The user interface and the setup, which you'll see later, makes it easy for the user to just write one line of code to do any of these types of estimates. One place where Stata is lacking is if you want to do any type of simulations. You could do it. It's very cumbersome. Where I think, on the other hand, R is easier to write custom routines to simulate situations. I think he's here in the crowd, but Mr. Neil Foltz, I think, has some experience simulating sample situations in R, and he could probably preach to the choir about this. If you needed compute power, I think nowadays a lot of power calculations are done through simulations. If you're proposing a design, you are submitting a grant to the NSF or the NIH and asking them for millions of dollars for your study. I think a sure thing is they'll ask you to do a power analysis before you design your data collection. R is great at that, and I think I'll advertise, if you're in that situation, Neil would be a good person to talk to. To help him along, give him lead time, because simulating power calculations needs a lot of planning and a heads up to do that. One point Andy brought up is this thing on the bottom. So you might be interested in subpopulations. You might be interested in gender differences, females in one subpopulation and males in the other. The way to do that in Stata is this one command, subpop. In R, it's subset. Here's a link to read the details behind the scene. The important point is you have to use these commands to create an estimate of your subpopulation of females versus males. This red highlight, it's not the same as if you just subset your data only to the group one and throw away the data rows of the males. When it comes to survey weights, the weights do something. If you just remove the rows, if you just set aside the males and focus your estimates on the females, your standard errors and intervals are going to be wrong. Because what you did is you threw away the weights attached to the males. It might seem like really small point, but it's important to keep in mind. The last thing I want to talk about is Chad Hazlitt, professor in political science at UCLA, joined at UCLA, who I think recently got promoted. He had this one article showing the pros and cons. When are situations where you should just fit a regression using fixed effects instead of an alternative regression that has random effects or multi-level models? So comparing a GLM versus an ME-GLM. In R, when should you use a GLM or a LME? It's worth checking that out. Long story short, I think it's easier to fit the GLM, and most likely it gives you the outcomes you're interested in, whether you have binary outcomes, smoker or non-smoker, positive mental health or poor mental health. On the other hand, the random effects, you can do a lot more with it, but there's a lot of extra steps after to post-process to give you what you really want. So it's more flexible to use random effects if you know what you're doing. So let's take a look at the side-by-side, how to get these different estimates you care about. On the left is Stata, on the right is R. So in this situation, in R, I went with that simpler route where I just fit a GLM with fixed effects. The outcome is, I think this was if you're a smoker or not. Yeah, or this one is. The outcome is if you smoke or not. We think that might be related to what's your age, what's your income, what's your ACT. So if you're familiar, if you learned it in class, you could use a binomial GLM. That just means you're estimating a logistic regression. So this one line equivalent in Stata is, you could use that survey GLM, but at the same time, I think behind the scenes, you can also use this logit command. It fits a logistic regression for you. One important thing is in survey analysis using Stata, you always have to prefix it with this SVY colon. That folds in the step you did earlier, right? Earlier, we told Stata what the weights are, what the strata is, because that's set up. Now, downstream, when you're computing your estimates, you're telling Stata when you fit this logistic regression, oh yeah, also incorporate the strata design and the weights. Same thing in R. We plug in the design we set up earlier. We set that up earlier here, right? We told it what the strata was, what the weights are. Here's a design object. You plugged it into a GLM model. I'll pause there if there's any questions about the code. Now we're getting to the interesting part. Before that, I gave the helpful workflow advice earlier. There's definitely missing data, most likely in every data set you work on. Workflow-wise, to make progress and prototype your code, just to meet deadlines, it's useful to set missing data aside with the very important reminder that you should revisit it when you have more time to correctly address how you want to deal with the missing data, whether you can argue not to impute it, or you can make an argument why some imputation methods are warranted. Everything up until now, we removed the missing data just so we can make progress on the code setup. Everything up until line 194, 190 here, operationally, we set aside the missing data. Now that we have more time to spend on what we want to do with the missing data, we can fold that in. Later, you'll see after we fold in the missing data, the analysis steps are very similar. It's just going to use these same estimate commands in R and similar commands in Stata. The extra step is just telling the program how you want to treat and deal and live with the missing data. So that's where we're shifting towards in the presentation. I'm gonna need to get some more water, but gives you a time to ask some questions. And I think tying back to what we'll talk about, but the earlier question Martha had about is, when should you assess the missing data situation in your context? I'll leave this up while I run for some water. All right.
Mike, there's a question in the chat as well from Shiva.
Right, excellent. Yeah, I saw that, and perfect question. Now that I'm rehydrated, short advice is use both. And if you have time, do a sensitivity analysis. Use both in the sense that tell Stata and R, if there truly is a sample design, the strata clustering and sample weights, fold that in. But at the same time, include the strata group ID as a variable on the right-hand side of your regression. This is assuming you're fitting a regression. Maybe it's better to see it in the code. So it might seem redundant to do that, folding in the Strata IDs in the design stage for Stata and R. Do that, but also additionally, if you're specifically fitting a regression, it's suggested that you also include the Strata group variable as a right-hand side regression independent variable or a right-hand side predictor. The thinking there is everything related to how your data was collected should be informative in your estimates. Informative is kind of a loaded term. One way to think about it is, did the Strata variable go into the decision in selecting the people into your data set? If you think it is, you should include that in your regression. I think there's some links and comments, which yes, there's a lot of alternatives to do that.
Sorry, can I ask a follow-up as well?
Of course.
Sorry, I'm sick, but I've seen a lot of papers that use weights in the descriptive table and then not at all in the rest of the paper. And I wondered if people were doing that out of convenience, but it seems like it's actually okay to use both. So if one of your predictors is the effects of single parenthood, for example, but the sample design oversamples single parenthood, then you could use it in, I guess foreseeably, you could use it in both the weights and the regression.
My advice is, yeah, incorporate the weights.
Okay.
If that weight you computed adjusts for oversampling in the sense that there might be some parents in your data set that appeared 3 times, or another way to think of it, if they had the potential where they were surveyed 3 times and this weight divides their data point by 3 to kind of adjust for that over representation, which is this representation stage. You should fold that in that Stata R setup where you're using a weighted estimate. I think what you might have seen where they produce output without the weights, as well side by side with estimates applying the weights, I like to think of that as a sensitivity comparison. It gives you an idea of what the weight is actually doing. How does your outcome estimate change in an unweighted analysis versus a weighted analysis? But keeping total survey error in mind, if that weight really factors in this adjustment for over representation, I think from just what I hear right now, I think it makes sense to apply the sample weights. And also, I think to tie it back to the earlier question, I do that weighted estimate. I think you should also use that weight as a right-hand side predictor if you're in that situation when you're running regressions. In your data set, that weight is just a column. If you use these survey routines, it applies it in the weighted estimate behind the scene, but you can also explicitly use that weight column as a right-hand side predictor. I think this ties in this question and that earlier question. Hopefully that gives you a sense of this.
Yeah, thank you.
Sure. I'll try to tie it into this idea of ignorable. Those earlier 2 questions, whether you should include variables that were used to sample your data, whether it was cluster or strata, if you think it's informative of your sample design, you should include it in your regressions. There's a similar thinking when you're trying to triage your missing data. It's called ignorable. Earlier, was your design variables informative? Here now in missing data, are there variables you collected that is ignorable? Does it tell you something about the people that responded versus the people that did not respond? And this is a little outdated, but every reference you see historically in the books uses these 3 scenarios: missing completely at random, missing at random, missing not at random. If you read some of the references, like the Little Rubin book, some of the current methods, I think some UCLA groups of researchers like using graphical models to impute. These 3 scenarios help you figure out what you should do. Maybe the diagram makes more sense if you're a visual learner. This gets at that idea of ignorable. I'll pause and let people read this. In the easiest situation, missing completely at random, let's say your health outcome you're interested in is Y. You have 50 people you selected in your sample, 20 people responded, 30 people didn't. This R variable is 1 or 0. 1 if you're one of the 20 people that responded, 0 if you're the 30 people that didn't respond. There's no arrow connecting the two, and in this situation, Z and R is ignorable. You can ignore any unobserved variables you did not collect, and throw away the 30 observations that did not respond, and only make an estimate with the 20 people that did respond. You could do that, but at a cost. Your estimate will be biased if you think you're in this situation, but you threw away information. What that means is your uncertainty intervals, standard errors, you're leaving money on the table. You could have narrower intervals to have a more precise estimate, but it's easy to do. I think it's the easiest thing to do. If you can make an argument that you're in this situation, missing completely at random, then only the easiest thing to do is you can just make an estimate using the 20 people that responded. It's not advised because you leave information on the table. The next step up is missing at random. This diagram here. You still might be interested in a health outcome. The 30 people that didn't respond, you think they might not have responded correlated to this measured variable in your data set X. Age. If your data set has age as a variable X, it's observed. What that means is it's observed. What that means is you have it measured in your data set, and you think age is related to whether they respond or not. You could use X as a predictor to impute the 30 people that did not respond. Here, that word of ignorable comes in. If you do not include X, it's not ignorable. If you include age to impute the 30 people that respond, it's conditionally ignorable. Conditionally meaning after you folded in age, it gives you a predictive relationship of the 20 people that responded and the 30 people that didn't respond. What if older people did not respond? You know, what if you're younger, you're more likely to respond? So that missing at random situation is here. The 30 people could be imputed by an observed variable you think is related to whether they respond or not. If you can make an argument that you're in that situation, I think it's a good idea to try out some imputation methods. That is one improvement over this situation. You are leaving less money on the table. Your intervals can be more precise. I'll save this for last. This is the hardest situation. Missing not at random. I think it's the hardest and most likely the most realistic situation that happens in the real world across every data set. Here, whether you respond or not, it has this connection, right? This relationship. Whether you respond or not, unfortunately, bleeds into this unobserved variable. Unobserved meaning you don't have it measured in your data set. The data set provider didn't collect it, or even beforehand, if you're designing a study yourself, you didn't have the foresight to ask this question on your survey, or it's just impossible to measure because of IRB restrictions. Yes, maybe in the real world, there's this relationship where, I don't know, your DNA, a crazy example, your DNA is related to whether you respond or not. IRB might be hesitant to let you design a study where you're collecting someone's DNA for good reason. It's PII. There's like a history where the IRB has for good reason, these requirements. If your outcome and whether you respond or not is related to this underlying unobserved, unmeasured variable, you're likely in this missing not at random situation. There are sophisticated approaches that try to address these points. It's hard to use, and I think you need to learn more about it. Take that course taught by Tom Bell in biostats, where I think you can learn a lot more about that. Are there questions about these three? I think we have 20 minutes left. We're close to the end. Then what I have next is trying out this one go-to imputation method that works pretty well in this second missing at random situation. And it doesn't hurt if you think you're in this missing completely at random situation. You could try it in this difficult situation, but like I said earlier, this is the hardest scenario to work with. So one method I like is something called mice. Usually I hate rodents, rats, mice, mouse. When you're dealing with missing data and you impute values, That's that one situation. Mice is good. It's good in the sense that both Stata and R have implementations of it. It runs pretty quickly. It works decent in many situations. Of course, you can find examples where mice breaks down, but workflow-wise, if I needed to impute missing data, I assess the pros and cons, and I need to do something about it. I need to impute data. First thing I would try is mice. It's a good benchmark. Even now, when people are suggesting newer modern approaches, mice is kind of the benchmark they compare their studies performance bake-offs with. So the acronym MICE is multiple imputation using chained equations. I kind of color coded it as this. Multiple, you run it n many times, 5 times. For now, let's just run mice once, m equals 1. What does one cycle of mice do? 1, 2, 3, 4, 5, 6. Say there's 7 variables in your data set. First, you impute the missing values in this green variable using all the other 5 variables. So impute the green variable with all the other non-green variables, and then cycle through every variable. That gives you one generation. If m equals 1, you have one data set that's complete. All the missing values are gone. You can do this as many times as you want. I think a rule of thumb is you can run the yellow mice generation 5 times, at least. Try 5. I start off with m equals 1 because it lets you debug any situations. It lets you specify what relationships you care about. There are situations where you should not draw this line. And that goes back to this 3 breakdown. The default settings, I think in Stata and R does this. If you don't tell it extra relationships you care about, it will use everything to impute. Everything will be imputed by everything else. Start with 1 generation. Spend your time to thoughtfully specify these relationships. Once you have a good sense on something you can defend, make an argument for why you did that, crank up the generation to create 5 multiple data sets that every data set has no more missing value. The idea of m multiple is now you have uncertainty between the 5 data sets. You can propagate that forward into your final estimate, and your final estimates intervals now fold in this imputation uncertainty. If you chain it all together, your final intervals have uncertainty due to sampling, why you chose 50 people out of 5 million, why did 30 people respond instead of where 20 people didn't. Now this uncertainty also folds in this imputation that you use to fill in missing data. I'll point out this book. He wrote the book on mice in R. Fantastic. And it's an ebook version too. Very helpful. Not to confuse you, I think in his book, M really means multivariate. I think it's a rebranding. In the first versions, M used to mean multiple. And I like multiple because it gets this idea where you could do it 5 times. Multivariate just means 1, 2, 3, 4, 5, 6, 7 variables. If you want to do a multivariate imputation, you're filling in all 7 variables at once. If you want to be really, really specific, just add a second M. M mice. Mice. So if you're reading this, just keep that in mind. Here's one difference. We'll take a look at the code right here. But you'll see side by side, up until now, R and Stata, the 1 lines of code kind of had a 1-to-1 match. But now when you're folding in imputation, it goes a little off the rails. There's 1 step in R that you need to do with 2 commands in Stata. There's 2 command steps in R that Stata just combines it in 1 command. But all of this is just saying you need to impute the missing data. You need to tell Stata what you want to do with the 5 copies of completed data. And the last step is how you move that into your final survey estimate. If you look at the last line, you know, that should be familiar to you. These were the commands we used earlier. What's new are the first step, the steps up top, filling in data, how you want to combine the 5 data sets, and then telling the program what to do with it. We could come back to this later, not that important, but goes back to that earlier point. I think R is useful if you want to develop newer ideas. That's harder to develop in Stata. Vice versa, Stata is more user-friendly if there's traditional or classical tried methods that you want to use. For example, I think R now has all of these new kids on the block prediction methods to impute missing data. 5 years ago, random forest was new. The cousin of that is boosting. You could now have neural network methods to impute. In a project with Rand, I learned there's a copula method to impute stuff. We looked at mice here. The Rand method, they have a package called gerbil. I don't know why they're sticking with this rodent, you know, the theme of rodents for imputation. At least I guess gerbils are cuter than mice. But the point here is I think R is easier to develop newer ideas, especially if that comes as a just suggestion from a reviewer or editor or PI or a funding agency. This happens for imputation, but to tie it back to the other situation, if you need to do power simulations. So let's take a look at the code. Before we do that, we're at the home stretch where at this stage, the final point of that outline, we're tying everything together. Up until now, we focused on the representation branch. How did people you selected, the 50 people you selected into your data set, upweight back into the target population you care about? Here, dealing with missing data, we've started to consider about the measurement branch. What do you do about the people that don't respond to specific variables? Can you do something about it? MCAR, MAR, not NMAR. What methods you want to try to impute these variables? You're now in the measurement branch. But like we'll see in the code and earlier, at this stage, both in R and Stata, you propagate all of this into your final outcome. Yeah, next is bonus stuff. So I think We're okay on time. If you want to stay for the bonus, great. I think the important stuff we've covered.
Mike, can I ask a question? If you could go back to that graph, the growth graph that.
Oh yeah.
It was the central. I mean, the guy, the guy through our presentation. So would it be correct to say that if for data to be missing completely at random, you have to assume on the right side, on the representation side, that non-response error is random, but that the missing at random refers more to the left side, where the response error to specific items could be random. Is that fair? Because I mean, I'm thinking if on the representation side you have a non-response error, there's no way that your data could be missing at random. Not completely at random, but not even at random.
Yeah.
Right, because you basically have people you don't observe, well, unless they're completely identical to people who respond. Yeah, okay. I don't know. I was wondering if there was an easy way to tie missing pattern to that graph, because as it's basically an assumption that you have to make about the data, so you have to have a sense of those bias and whether you can make a valid assumption that it's missing completely at random or at random before you go on to more complicated things.
Pat's assessment exactly right, and I think that's why this TSE flowchart helps you figure out what side you're on. One part that confused me, and I think makes its way into Patrick's question, there's this non-response error that goes from the sample you selected, like 50 people, but only 30 people respond and 20 didn't. But if you flip to the different branch, it looks like something similar. It's kind of covered. Let me go back to the first one. You see it here.
Yeah.
They're related, like this error here, the processing or processing error versus this non-response error. They're related where you can and you should make this thought experiment and argument to figure out what situation you're in for both of these bubbles, both of the processing error and the non-response error. One thing that helps me think about why the non-response error is on this right-hand representation side versus this processing error is on this left-hand measurement side is there's two ways you can there's two methods, post-processing methods you can use to deal with missing data. Let's think about this data with 7 variables. If the 30 people with 7 variables, all 30 people miss these 7 variables, you can re-weight, you can redistribute their weights to the 20 people that are responding. So that's a re-weighting method that tries to do this non-response error, which falls under this representation branch. On the other hand, if you try out mice, where for these 50 people, 7 variables, it's like a scatter where for those 30 people, you have like 5 observed variables, but those 30 people are items, like their cells, their specific values for these 2 variables are missing. You're imputing these cells using mice. I would just shoehorn that into this processing error where you're making a mismatch with how you're imputing specific variables to the edited version. That's how I like to think about it. And then with talks with this diagram, this comes up, and yeah, there's this. You would think they're related and different. The way I look at it, it's what post-processing statistical technique do you use? Do you use a reweighting method, which I would fall under this representation category, or do you use this kind of variable imputation method where I would put under the measurement category? But in both situations, this assessment still applies, the MCAR, MAR, MNAR. Hopefully that doesn't confuse things more. I think there's comments in the chat. Right, Neil, I think I annotated it later. All of this is reweighting where you're adjusting entire rows of people. If you have, I don't like, it helps to visualize it, but if your people are rows in a spreadsheet, it's not a good metaphor, but a lot of these reweighting methods on the representation, you're redistributing rows, entire rows of people. Measurement kind of deals with the columns, how you want to edit cells, at least in this stage. Up at the top, there was that hypothetical line, right? That was like domain expert philosophy. Does the construct you care about, are you able to measure it with your survey questionnaire? There's that hypothetical line there. Hopefully that answers your question, Pat.
Yeah.
I have to wrestle with this also. It's tough. Because yeah, at this stage, when you're imputing it, it combines everything. We'll take a look at the code right now. Left hand is Stata, right hand is R. I think R was easier because you impute first. You run mice, default, every variable, every item column is imputed by every other variable. Notice here, I'm telling R, use the raw data. It's ignoring the raw survey design. It generates 5 completed data sets. So now I have 5 data sets that are imputed in a list, a shopping list of 5 data sets. This is what I'm gonna feed into the survey design here. Yeah. You have a list of 5 completed data sets. That's what you're plugging into the survey design. Our friends, the Strata ID and the weights make its reappearance here. Here you have 5 survey designs that match the 5 imputed data sets. That's what this imputed design is. Then everything's familiar. Compute the means, the totals using this imputed design. If you want to look at relationships between variables like an outcome and right-hand side variables, you can fit regressions. To tie it back to the earlier question, we don't see it here, right? That recommendation I suggested is we should add that straight variable as a right-hand side predictor. Where was it? And the weights. Include these 2 variables here. So that's R. The Stata version, similar, but there was that change in order of operations. You set up your imputation. You impute with k nearest neighbors. Or you can use mice, chained equations. That's what it's here with. Do it 5 times. Here's where you can control what relationships are used to impute. With that setup, here's the difference. You have to use this MI prefix to tell Stata the imputed data in combination with this SVY prefix to remind Stata that there was a survey design in the background with strata and weights. So in Stata, these two parts are combined in this one line where, let's jump back to R. It was done, you could do it separately, but at the very end, the survey stuff absorbs all of the imputation and design setup. Is there any questions about the code? Hopefully this is helpful. I'm not running the code here because I don't think that's helpful. If I ran this live, all you'll get out of it is you'll see the result printed out. Both of these code files are up. You can get to it through the slide, which gives you the benefit of running it yourself. I'll save time for this last step, calibration. And it ties back to that answer I gave Pat on calibrating or adjusting weights on the right-hand side of that representation branch of the total survey error. Calibration is a post-processing method traditionally used here in this gap between coverage error, where your target population that you have in mind, everyone in America, versus your sampling frame, email addresses you have, or mailing addresses you have. You could use calibration to make your list of email addresses or addresses redistribute the row weights so it looks like an external population third-party data source. Doing that would fix or adjust for coverage error, which is this bubble here. But calibration is all just a technique. It's a post-processing technique, which some people could also use for this mismatch between the 50 people you sampled, 20 people respond, 30 people don't. You use calibration to redistribute the 30 non-responding row weights to the 20 people that do respond. So calibration redistribute weights from the row-wise. And to drive it home, other imputation methods fills in variables cell-wise, which you can kind of think of as editing. You're editing the data. When we're focusing on calibration is this mismatch between target population in blue and your frame that you have. Email addresses, if you're Kevin O'Leary, Mr. Wonderful on Shark Tank, with his database of email addresses, you have this purple bubble. Kevin might have people in his email database that he does not intend to make a survey estimate to. That's ineligible. For example, he might have email addresses that come from an organization. He can't sell stuff to Gene Block at UCLA.org. He might have that in his database, but if he's taking a product survey of things to sell things to, that might be ineligible. He picks 1, 2, 3, 4, 5, 6, 7 people from his purple list of email addresses. He picks these 7 individuals in his sample. He understands there's ineligible people and people he's missing in the population he cares about that do not show up in his email database. So one way to adjust for that is using calibration. Essentially, you're reweighting, which is what you see here. The blue is a third-party distribution of the population. You form these 3 strata groups. It can be by age. age strata group 1, age strata group 2, age strata group 3. In group 1, you form this ratio, which is the distribution of your sample in yellow. You squash that down so it matches the population ratio in blue. You do that within each strata group, age group 1, age group 2, age group 3. Then you make a weighted average to your final post-stratified estimate. You're trying to make Arnold Schwarzenegger look like this character in One Piece. So hopefully this is a crash course in calibration, how everything kind of falls into total survey error. Yes, here was that point home. Representation deals with rows. How do you want rows of your sample? How it was selected down in this direction from the population down into your data set. Vice versa, going up is how you're upweighting your sample to match the population you care about. In the other branch, you're spending thoughtful time on the outcomes you want to measure and how to impute any missing outcomes, and if you're making any processing error. Everything combines into your final estimate. With that said, thank you. It's been a long workshop. Hopefully it was helpful. We're 10 minutes over. I will stick around if there's questions, and if people want to go back to different slides, I'm happy to do it. So thanks everyone, and thanks Esmeralda and the question askers.
Thank you, Mike.